Hi, my name is Brian Caffo, and this is the Regression Coursera class. And today we're going to talk about count outcomes and Poisson GLMs. These slides were originally Jeff Leak's from his data analysis Coursera class. The class is co-taught by Jeff and Roger. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so the key idea here is that many data take the form of counts, and that we can't necessarily model counts in the same way that we model other things with linear regression or binary regression, the two topics we've covered so far. So some examples of counts are calls to a call center, number of flu cases in an area, number of cars that cross a bridge, and so on. I work in biostatistics, so we deal a lot with counts that are of the form number of cases of a certain sort. So this, for example, these kind of Poisson models are highly used in infectious disease epidemiology for modeling counts of disease outbreaks. The data may also be in the form of rates. In fact, I find it difficult to think about Poisson data without thinking about it in terms of some rate or some monitoring time. So what we mean by rates then is a count is a count per unit time. So for example, the classic variable that follows the Poisson model is radioactive decay. So this is counts of radiation detection hits on a detector. That count is, of course, dependent on how long you're running the detector, right? So it's not relevant to talk about the count without talking about how long you monitored things. So it's count per unit time. And I would also say that the raw percentages can be modeled as count data, they're obviously counts, but the percents, which kind of seem like binomial processes, can be modeled with Poisson models, especially when the probability is very low and the sample size is very large. That's a classic case where we simply model that data as if it were Poisson, even if there is no bound on or even if there is a hard bound on the number of possible successes. So, and we're going to talk about a lot of these different things today. Linear regression with transformation is an option, and we'll go over logging the outcome just because it's an important special case. So the Poisson distribution is a particularly useful distribution for modeling counts or rates. Here I'm defining a rate as a count per some monitoring time. So some examples of the Poisson distribution: so web traffic hits, incidence rates in epidemiology, binomial type processes with small p and large n. And there's a huge use of Poisson models for analyzing contingency table data. We won't cover that, but people do that. So the use of so when I say a contingency table, you have let's say, I don't know, something like hair color. Let's say a person is blonde or not blonde, and eye color. A person is blue-eyed and not blue-eyed, let's say. And if you were to sample a bunch of people and just tabulate the counts of these things, that would be a so-called contingency table. At any rate, the contingency tables are often, I would say, mostly analyzed with log linear models, Poisson log linear models. So hopefully everyone's had the inference class or is taking the inference class at the same time. But if not, let me just give you a couple of quick things about the Poisson mass function. So we say a random variable x is Poisson T lambda if the probability that x takes on a specific value is t lambda to the x e to the negative t lambda over x factorial for x a count starting at 0 and going to infinity. Often, in many cases t equals 1, so you might specify this in terms of lambda. So the mean of the Poisson random variable is expected value of x equal to t lambda. And so also, so of course that means the expected value of x over t is lambda. And then the variance is equal to the mean. That's an interesting fact about the Poisson. And then the Poisson tends to a normal as t lambda gets large, which means if you fix lambda, then this means as t gets large. So if t is some sort of monitoring time, right, then that t is the very natural thing to get large. Lambda, by the way, you can see right here, lambda, by the way, right, is interpreted as expected counts per unit time. So lambda has units. That's a nice thing. It's a units per time. All right, let's see. Let's look at the Poisson distribution for a couple of different values. So here I'm just plotting a Poisson with a lambda of 2, and in all these cases t equals 1. So here I'm plotting a lambda of 10, and here I'm plotting a lambda of 100. I have to use a different horizontal axis scale because lambda of 100, right, the mean is 100, the variance is 100. That shifts the distribution substantially along the x-axis. So notice there's a different scale. You can see, kind of what it looks like here, what it looks like here, and then also you can tell that it looks almost exactly like a Gaussian by the time you get up to lambda equal to 100. So we don't, I don't want to go through the math. In the other class we go through the math. In boot camp 2, I think, in my other class I go through the math. But here I'm sort of showing that the mean and the variances are equal numerically at least. So I'm going to take x out to infinity. So for the purposes of this example, infinity is, what is that, 10,000? 10,000. But this goes pretty fast, so you could do 100,000 if you wanted to. And you plug in whatever lambda value you want, and then our mean is just the sum of the x values times the mass function values, right? And my sigma squared is just the sum of the squared deviations around the mu value times our mass function values. So here's my mu and my sigma, and of course it's 3, exactly equal to the lambda we used for plugged in as the theoretical value. Okay, and then you can, if you know the expansion for E, then you can actually prove this rigorously, but maybe not.